Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 9th, 2026, which was just 4 days ago. It introduces a generative evolutionary framework that uses large language models to co-evolve paired operators for optimization problems, achieving a 0% gap on the CVRP 200 benchmark and outperforming strong classical solvers. The paper is titled G-LNS, Generative Large Neighborhood Search for LLM-Based Automatic Heuristic Design. And, as we'll see later, the performance gains and the speed improvements over existing methods are quite remarkable. For those interested in the implementation, the authors have shared their code on GitHub. So Figure 1 illustrates the core difference between this framework and previous approaches. On the left, traditional methods rely on constructive rules that cannot backtrack, or guided local search with fixed operators like to-opt that easily get trapped. In contrast, the right panel shows the G-LNS approach, which generates coupled destroy and repair operators. By partially dismantling a solution and intelligently rebuilding it, this method enables the large structural jumps shown at the bottom, which are essential for escaping deep local optima. Alright, Figure 2 details the framework's cyclic workflow. It starts in the top left with initialization, where the system creates two distinct pools of operators, one for destroying solutions and one for repairing them, using both expert seeds and LLM-generated logic. Next, the evaluation phase on the right tests these operators by dynamically pairing them up, recording which combinations succeed in a synergy matrix. After low-performing operators are pruned in phase 3, the evolution phase in the bottom left takes over. Here, the LLM uses the synergy data to perform mutations in specific crossovers, generating new, high-performing operators to replenish the pools. Moving to the results, Table 1 compares performance on the traveling salesman problem across sizes from 10 to 200 cities. The key metric is the optimality gap, measuring the distance from the best solution found by the LKH3 solver. On the hardest task, TSP 200, prior methods like fund search and EOH struggle with gaps over 17%. In contrast, the bottom row shows G-LNS cuts this error to just 1.3%, proving its superior scalability. Well, Table 2 breaks down exactly which components drive these results through an ablation study. Up top, the full G-LNS model achieves a tight 0.37% gap on TSP50, drastically outperforming the standard adaptive LNS baseline. The middle section then shows what happens when we strip features away. Removing mutation or homogeneous crossover causes the error to spike, highlighting the need for logic fine-tuning. Finally, the bottom rows confirm that the adaptive weighting system is essential, as using flat or aggressive static weights significantly degrades the solution quality. Transcript. Okay. This table extends the evaluation to the capacitated vehicle routing problem, or CVRP, which is significantly harder due to capacity constraints. Up top, the classical OR tools solver handles small instances perfectly, but slips to a 1.27% gap on the 200 node task. The middle section shows that other LLM methods struggle even more, often missing the optimal solution by double-digit percentages. In contrast, the bottom row highlights that G-LNS excels at scale, achieving a 0% gap on the largest instances and beating all baselines, annotations. So, Figure 3 investigates the system's learning curve and efficiency. On the left, the evolutionary progress chart tracks the best operator score over 200 generations. The steep initial drop suggests the model quickly masters the fundamental logic, followed by a steady refinement phase where the variance narrows. Then, on the right, the evaluation progress chart compares convergent speeds on the 100 node vehicle routing task. The red curve for G-LNS dives much faster than the baselines, reaching optimal solutions in just 70 seconds, which is drastically faster than the 1100 seconds needed by the Monte Carlo tree search approach. Wrapping up, G-LNS proves that large language models can drive structural algorithmic innovation rather than just parameter tuning. By intelligently co-evolving destroy and repair operators, the framework solves complex vehicle routing problems with a 0% optimality gap, outpacing both classical solvers and prior learning-based methods. This suggests a promising future for automated heuristic design and high-dimensional optimization. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.